Hello everyone. Today we're going to be talking about my MAT 229 Project 1. Uh, this project is a Hill-Cipher machine written in Python. It allows you to encrypt whatever text you want and to decrypt whatever Hill-Cipher you want, provided that you know the key. It also creates an automatic step-by-step document written in Latex that shows you the steps to decrypt the specific cipher that you inputted. So let's take a look at how the program works. If I run this cell right here, it's going to first ask me whether I want to encrypt some text or decrypt some text. So let's see how encrypting some text looks like. We first press E. We simply enter the text that we want to encrypt. We enter the key that we want to use to encrypt that text, and we get back our encrypted text. Now, what if we want to decrypt that text back? You do the same thing. Instead of choosing encrypt, you choose decrypt. You enter this encrypted text, and then you enter the key, which we know is ciphering. And if you don't know this key, then it's going to be quite hard to break the cipher. That's the whole point of a cipher. And you get back I am big. Now, what about if you want to create a LaTeX document that shows you how to decrypt IamBig? Well, you use this feature called Auto LaTeX, which I've programmed and which allows you to create a LaTeX document for each specific cipher that you enter. So let's use the example that the professor gave us in the project description. So let's say that you want to decrypt this bunch of text. We know that the key that we need to use is ciphering. We get back math is my life, which is the correct output, but we also get back this dynamically generated PDF that has all the steps needed to decrypt this cipher. Let's take a look at the PDF to fully understand how this program works. So as you can see, initially there's an introduction that explains that this project implements a Hill-Cipher machine which automatically generates LaTeX reports to decipher user-entered Hill-Cipher step by step. If you notice, it says that we will be deciphering, and then this is the key that you entered as an input to the console, and this is the cipher that you entered, and this is the key that you entered to decrypt that cipher. The second heading is called the Encryption Matrix, where it tells you how to first formulate an encryption matrix for a specific key. So it says that we use this lookup table, which I got from Wikipedia, and your key ciphering, and you replace each letter in your key with the number that it corresponds to, and then you create a matrix that is 3 by 3 in the order of your key, which ends up being 2, 8, 15, 7, 4, 17, 8, 13, 6 for our matrix. The next step is to find a decryption matrix, because we are not really encrypting text here. We want to decrypt this cipher that has been handed to us. So to create the decryption matrix, you simply take the inverse of the encryption matrix modulo 26. So the way that this program does it is it uses Gauss-Jordan method to find the inverse. If you look at this first step right here, you first calculate the elementary matrix 2, 1, and 3, 1 that eliminate the positions 2, 1, and 3, 1 in the augmented matrix M, which is this matrix, our encryption matrix, with the identity matrix. And the result that is shown clearly shows that 2, 1 and 3, 1 are now 0, meaning that they've been eliminated. You keep calculating matrices like these, 3, 2, 1, 3, 2, 3, 1, 2, 2, 3, 1, 3, all the way until all the elements other than the elements in the diagonal have been eliminated. Then you turn the elements in the diagonal into 1 by dividing the whole row with them, which is simply the end of the Gauss-Jordan method to find an inverse. You can see that end step over here, where this is the diagonal matrix, and the diagonal matrix is multiplied with this reduced matrix to give you the identity matrix on the left block and the inverse on the right block. However, now the tricky part starts. The inverse is a normal inverse, but we need to find a modulo 26 inverse. The way that we do it is we first multiply this matrix by its determinant, which is 1, 2, 4, 3. Then we multiply it by the modular inverse of its determinant, Now, the modular inverse is a number with which you multiply the determinant, and if you take modulo 26 of that result, you get 1. So 5 is the modular inverse in this case, and then you write the resulting matrix modulo 26. And that matrix in this case is 3, 7, 16, 2, 6, 17, 9, 8, 20. And that is our inverse matrix or our decryption matrix. So the next step, once we've calculated our inverse matrix or our decryption matrix, is we break our cipher into chunks of 3 and we multiply the decryption matrix with each of these chunks. If you look at the first step, that's exactly what we're doing. We're taking X, R, and C, and we're multiplying our decryption matrix with it and writing the result in modulo 26. If you convert that back into characters, then the decrypted chunk is MAT, which notice the LaTeX document that is automatically generated also gives you. You do this step for the rest of the cipher until you've decrypted all of it. And then at the end, you get this result, which is math is my life. So that's the math which is behind a Hill-Cipher. Let's look at the Python program that makes this LaTeX document and this encryption and decryption possible. The complete Python code is publicly available on my GitHub for those interested in taking a look. We're just going to go through an overview of the main function that calls the other linear algebraic subroutines. If you've used Python before, you're going to be very familiar with the syntax. If you haven't, the syntax still shouldn't be too hard to follow, particularly if you've used another programming language or a math programming language like MATLAB. The Python syntax is quite similar. So let's focus specifically on this function called runHill, which you've seen multiple times. This is the function that is called whenever we want to decrypt or encrypt a cipher. Initially, the user is asked whether they want to encrypt or decrypt the cipher. Let's look at what the program runs if the user wants to decrypt a cipher. So that is if choice is equal to D. Let's look at that block. So here, if choice is equal to D, then the program runs this algorithm where it decrypts your input. The first block of code that you can see over here simply takes the input. It takes the encrypted text and stores it into cipher variable. It takes the key and stores it into the key variable. The second block checks if the key is not length 9. And if the key is not length 9, then this is an invalid key and the program raises an error. The next step is the program calls this routine that I've written called get3length phrases, where it breaks down the cipher into chunks of 3. Remember, we need to break it down into chunks of 3 because we need to multiply each of those chunks with the decryption matrix. Next, the program loops through these chunks. So these phrase in 3 phrases, which is a list for those familiar with Python. And it calls the decrypt cipher subroutine, which is also an algorithm that I've written later on in the code that basically decrypts that individual chunk and stores it in this text variable. It does this with all the chunks until it can recombine them into this one text variable, and then it prints right over here the decrypted text. This last block generates the auto LaTeX document if you set L out equals to true when you're calling runHill. So basically, if you configure runHill to generate a LaTeX document, it will. And the way that it does it is through this method or this function called generateLaTeX, which is available to see in the full code on GitHub if you're so interested. Another method to note is this inverse mod 26 method, which simply calculates all the elementary row matrices using pivot positions. At the end, it calculates the determinant, and then it does the modular inverse steps, and it returns back the augmented matrix, the modular inverse of the augmented matrix. So that's my project. It's a Hill-Cipher machine that creates LaTeX documents to show how to decrypt a specific cipher step by step, and it programmatically decrypts or encrypts ciphers depending on user input. Thank you.